Now we're going to look at some general trends on the periodic table. The first one that usually comes to mind, it comes up a lot in chemistry honors, is called ionization energy. Ionization energy. And the basic definition of this is the energy required to remove an electron. And from that you probably get a pretty basic understanding of what ionization energy is. But to really understand it, we need to define this root right here. What is an ion? Now an ion is an atom or molecule in which the protons don't equal the electrons. So an atom or molecule where protons don't equal electrons. So let's look at some examples of ions. Let's see here. How about hydrogen? So you have this hydrogen atom, and it loses an electron, which means it becomes more positive. So we'll get H plus here. This is what they call a cation, because it has a positive charge, meaning that it has more protons than electrons. And then let's look at a different type of ion. Let's see, how about chlorine, Cl. Cl gains an electron, so therefore it has a negative charge. We call this an anion, because it gained a negative charge. Now, how some people differentiate these, I usually look at this A right here, an anion. A is a prefix that means opposite. So I usually remember that the opposite charge is negative. Now, other people remember it by this T right here in cation. It kind of looks like a plus sign. So that would be the plus sign in hydrogen, and that would make it a cation. So those are your basic types of ions, and now you know what ionization energy is. But if you look at the definition, ionization energy really is the energy that it takes to turn it into a cation, to make a cation. That's what ionization really is, because you're taking away an electron and therefore making the atom more positive. Alright, let's go down and actually look at the periodic table. Now let's look at these group 1 elements right here, lithium through cesium. Lithium only has 3 electrons, meaning that it has 1 extra electron. One shell is full and one shell only has 1 valence electron in. So it wants to get that magic number, have a complete full outer shell of electrons. So it really wants to get rid of that last electron. So if it really wants to get rid of it, it's not going to take much energy to get rid of it. So it's going to have low ionization energy. Now let's look at the other side of the periodic table at, let's say, neon right here. Now neon has a full outer shell of 8 electrons, so it really doesn't want to give any away. It's just floating happily in space, and it's kind of hard to get some away from neon because it's such a stable element. So over here, since it's going to take a large amount of energy to get that electron away, we're going to have high ionization energy. So with that being said, the general trend as you're going from left to right on the periodic table is you're going from low to high ionization energy. Alright, So now let's look at it going down the periodic table. So lithium here only has 3 electrons, so that means it has a relatively small electron cloud. Now on the other hand, look all the way down here. Cesium has 55 electrons, so it has a relatively large electron cloud. Since these electrons, the third electron in lithium, is closer to the nucleus, it's more attracted to the nucleus. But on the other hand, cesium has 55 electrons, so that 55th electron all the way out there has a weaker attraction to the nucleus than this one does up here in lithium. That being said, up here in lithium, we'd have high ionization energy, whereas down here in cesium, we'd have low ionization energy. So the general trend from going to the top to the bottom of the periodic table is you're going from high ionization energy to low ionization energy. So if you look at the whole wide scope of things, the general trend here is a line that goes all the way up here, just like that, from the bottom left corner to the top right corner of the periodic table. So that's the general trend. Now let's go look at a chart of ionization energies. Here in this chart of ionization energies, they're plotted in electron volts, which you can convert that to joules if you really wanted to. And so let's take a look at helium. Helium, as I said, is a noble gas element, and it has a full outer shell of electrons, meaning that it's really hard to get one of those electrons away. So it has a very high ionization energy, almost 25 electron volts. As you can see, neon and argon also have a very high ionization energy because they're noble gas elements. Now let's look down at the bottom of the chart. Can anybody guess what this element is? That's right, it's lithium. Lithium is all the way down there at 5 electron volts because remember, lithium had 1 extra valence electron and it wants to have a perfect shell, so it really wants to give that away. So it has a very, very low ionization energy, as does all the other group 1 elements. And you remember the general trend from going to the top to the bottom of the periodic table? You can see it right here in the noble gas elements, going from helium all the way down to radon, because helium is at the top of the periodic table, therefore it has a higher ionization energy than radon down at the bottom of the periodic table. Now, some of you may be wondering why these spaces get larger as we go across. Here you only have S and P block elements. Here between neon and argon, you also have S and P block elements. But going from argon to krypton, the space gets bigger. That is your SP and D block elements. If you look from xenon to radon, the space is huge. This is your S, P, D, and F block elements. So that's about it for ionization energy.